All right, in this video, I'm going to cover section 3.7, hypergeometric distribution. So hypergeometric distribution in here, so the hypergeometric distribution means that the number of the random variable, discrete random variable in hypergeometric distribution represent the number of the success, um, the in a sample with a size lowercase sample. And then, but the sample is selected randomly without replacement. Okay, so we deal with the we assume that uh, we deal with the Bernoulli trials, so that we expect only two outcomes for each trials, like the binomial distribution, the geometric and negative binomial distributions. But the key point is this: we when you select the objects, uh, the since the replacement is not allowed, that affect the probability mass function of the hypergeometric distributions. So let's take a look at this. You see the hypergeometric distribution, a general formula for computing probability when samples are selected without replacement. So you see that here a lot of the letters use. So you need to clearly understand the meaning of each letters. Okay, so capital letter N represent the set total number of object in a population. Okay, you can say populations, and then the K, the capital letter K, that's the number of object classified as successes in the population. Okay, then n minus k, that's going to be what number of object classified as failure. So and then we're going to select the object to construct the sample randomly without replacement. Okay, so now then the k what the lowercase n, that's the sample size. The lowercase n must be less than or equals capital letter N, the total number of the object in a population, right? And definitely then number of object classified as successes should be less than or equals what total number of object in the population. Okay, so that makes sense, right? Now what's the random variable? The meaning of random variable in the hypergeometric distribution, I told you that's the number of successes in the sample. Okay, so now then the PMF, probability mass function, f of x of the hypergeometric random variable is defined by like this. So combination of k and x, and then combination of n minus k and n minus x divided by capital letter N, combination lowercase n. Yeah. Um, so first of all, let me explain why x, the range of x is like this. So let me explain about this one by using the example in my handout here. Okay, so just think about this. Days production of manufactured parts is 850. Okay, and then number of parts that do not conform to customer requirements 50. So out of 850, so let's say 50 parts are the non-conformed. Okay, so now then let two parts are selected at random without replacement. So now, so what we selected two parts. So that's gonna be what sample. Okay, so sample size 2. Okay, but we'll change the sample size. Okay, later. So now then, so capital letter N is 850, and then capital letter K. I know it sounds weird, but let's say a number of success. Uh, the success means that the parts do not conform. Okay, so then the let's say the capital letter K is the 50, right? So now then let's say A denote the event that the first part is non-conforming, and then let's say B denote the event that the second part is non-conforming. Since the replacement is not allowed, we have to apply the what conditional probability. So P of A going to be 50 over 850. That's obvious, but probability to calculate probability B, then we need to apply the what we need to use conditional probability. Okay, P of B bar A, which is 49 times 849. Okay, so now then, so what's the x? X is what? In a hypergeometric distribution, x is number of non-conforming parts in the sample in this example. So probability x equals 0 gonna be what? Probability that both parts conform. So 800 is 850 times 799 over 849. It makes sense, right? But why just the denominators change? Because we don't allow to put the part we select the first trier back. Okay, in when you select the second one. So P of x equals 1 is we consider two cases. When you select the first part was the non-conforming, or first part is conforming, right? Okay. So I mean, oh, never mind. I'm sorry. So yes, right. Okay. So then the probability, then we have what we calculate the probability that P of B bar A prime, okay, which is the what A prime is uh, um, the non-conforming, right? And then P of B prime bar A, okay. So then P of B bar A prime is just gonna be what 800 or 850, okay. So now then the yeah, see, I'm sorry, I was confused. Let me see. Okay. Non-conforming, yes. Okay. Yeah, I think let me see. Was confused. Yeah, so the B is the event that we in a second trial we select the non-conforming part, right? And then so A prime, since A is the what event that in the first trial we get the non-conforming part. So A prime means the what? The complement of A. So A prime means the trial. First trial we select the conforming part, right? So similarly, B prime is the conforming, A is non-conforming. So then that's going to be equal to calculate this one. We calculate the P of what? The let me see, 800 P of what? Let me see. Since the we're gonna calculate the probability that we select the first trial, probability first trial we select the component part, which is 800 over 850, right? And then second trial we calculate the probability that we select the non-component parts, given that we already select the component part in the first trial, which is 50 over 849, right? And then P of B prime bar A is going to be what P first one. In the first trial we select the non-component part, which is 50 over 850. That's a P of the probability that in the first trial we select the non-component part times, and then what we second trial probability that we select the component part, which is 800, given that we already select the non-component part in first trial, which is that is 800 over 849. Okay, this is 0.111. Okay, so now then P of x equals 2 is this. Similarly, we can this. So now then, so we're gonna manually we calculate these probability, but using that formula we can easily figure out that probability using that PMF. Now then let me figure out the range of x, wide range of x like this in this using this example. Okay, so think about this one. Let's say this is represent the population. Okay, let's say n is I mean daily production. Okay, manufacture the parts. Okay, so n equals 850. Okay, so let's say here's number of the parts do not conform, non-conforming parts. Say k is 50. Okay, so and then n minus k. I mean this is a number of success, right? Number of failures here. Okay, n is what so n minus k, right? Which is the 800, right? Okay. Okay, so for example, let's say we select the parts randomly to get the sample like this. Okay, maybe. Okay, just for example. Okay, just sample. Okay, so n, sample size n right here. So now then what? The think about this. What if n is just you know, let's say n is for example n equals yeah, so maybe just 30. Okay, just example. Okay, so it's 30 here. Then the x, which is the in a hypergeometry the random variable, the x represent the number of successes in the sample, right? And then x can be what maximum here 0, could be 0, right? That's a minimum. Maybe in the sample there is no the parts which is non-conforming, right? Okay, maybe in the number of parts in this area is 0, maybe. Okay, even though n equals 30, maybe we just select the 30 parts in that area, right? In that region. Does it make sense, right? But you know but let's figure out this one, n minus k. Okay, so what is this? This is what? This is equal to, okay, actually n minus n plus k minus n, right? This is exactly the same as the one of the expression in the range of x shown in the lecture note, right? Okay, so now we see that why how we got this one, n plus k minus n. This is actual difference between n and n minus k. Okay, so now then the what if n equals give me a second, I think what if n is not 30 but lowercase n, the sample size is maybe greater than 800. Okay, what if n equals 10? Okay, then definitely, since the total number of the object classified as failure is 800 and the sample size 810, then definitely 10 object out of 810 must be object classified as successes, right? Then the hypergeometry random variable must start from, I mean, minimum number of success going to be 10, right? So the in generalize this one, we're gonna get this. Actually, n minus k when you calculate this one, because what we saw here. So n is 810, and then n capital N is what 850, and the minus k is 50. That's gonna be what the 10, right? So that's why we got this one, n plus k minus n, the maximum. Okay, maximum right here. Okay, so now, so if n is greater than sample size is greater than n minus k, which is the total number of the object classified a failure, then automatically we select this one. If the sample size is the less than the 800 total number of the object classified a failure, then we select the 0. Okay, through the what? And then look at the my lecture note. We see this one, minimum k and then n. Similarly, we can figure out why we got this one, because think of the using two cases. N is 30 and n equals 810. If n equals 30, then what? So then what? The maximum, possibly maximum number of object classified as successes in that sample will not be exceed what, 30, right? Okay, so now the k is, when n equals 30, the k is 50, n is 30. Do we have to select the 30 x maximum value of x must be 30, not 50, because it's not sample size is 30. What if n is 810? Then what? 810. Then what? Since this guy, that number is greater than 50, so what? The geometric random variable x, the maximum value of x could be 50. Okay, this makes sense, right? So in that the n is 810, then 50, and then 810 minimum. Okay, then which number is the minimum? This one, right? We select this. Okay, that's why we got the that expression in the range of x in the handout. Okay. All right, so let's take a look at the textbook. I see example 2.32, 3.23, and 3.24. Okay, and then see. So we're gonna see mean and variance of the hypergeometric distributions too. So see 3.23, simply without replacement. The computation at the start of this section can be reanalyzed by using general expression in the definition of hypergeometric random variable. That is this one. So you see in my lecture note, we so example about the parts manufactured. Then we select the two parts which are non-conforming, right? So we calculate the P of probability x equals 0, which is f of x 0, right? F of 0, right? P probability x equal 1, this is f of 1. P of probability x equal 2 is f of 2. So using we calculate this one using the formula of PMF of hypergeometric distribution. Okay. So now then the example 3.24 and the parts from suppliers. So a batch of parts contain 100 from a local supplier of circuit board and 200 from a supplier in the next state. If 4 parts are selected randomly and without replacement, what is the probability they are all from the local suppliers? Okay, so I told you, once you just get the problems, you need to figure out which distribution you have to apply. Okay, is this problem about hypergeometric distribution or geometric distribution, negative, binomial, or uniform? Okay, or before doing that, you definitely need to figure out, is this problem about discrete or continuous random variable? We'll see continuous random variable in the next chapter. But so now see, as you can see that so in these problems, the number of parts are 300, right? 100 from the local parts, and then the rest of them from the supplier, right? So now this problem says that we select the 4 parts randomly. So sample size must be 4. Okay. In the K, the parts from the local supplier is 100. So how come, why the K is 100? So because the problem says that the what is the probability they are all from the local supplier. So the parts from the local suppliers should be considered as the what object classified as success. Okay, so that's why K is 100. And then PMF going to be this, the 100 x times 204 my x and divided by 304. I mean combinations. Okay, so using this formula you can solve the problems. I mean probability that x equals 4, that's going to be what, f of x equals 4, right? Oh, f of 4, I'm sorry. So, okay, all right. So then I told you how to calculate the combination using calculator. Just see a previous video. Okay, and then the second problems is this: find out the give me a second. So the second problem is to find out the x is greater than or equals to. I mean, what is the probability that 2 or more parts in the sample are from the local supplier? So then we have to calculate this. Then we have to calculate probability that x equals 0. Okay, and then 2. I'm sorry, it should be 2, not 0. Plus probability that x equals 3, and then plus probability that x equals 4, which means that what? We need to calculate f of 2 plus f of 3 plus f of 4. Okay, so or mathematically we can the expressions, return the expression I equals 2 to I equals 2, 3, 4, and then f of I. Okay, maybe you can say that, or either one just fine. And then the last problems, last question in this example, what is the probability that at least one part in the sample is from the local supplier? That means, well, at least when you see at least, then you gotta use a rule for complementary. Okay, so then we have calculate this one, probability that x is greater than 1 equals. That's what a problem is asking, right? This is equal to 1 minus probability that x equals 0. Okay, I mean, you can calculate this one. That means what? You have to calculate f of 1 plus f of 2 plus f of 3 plus f of 4. So that require a lot of computation, right? So instead of that, we're going to compute this 1 minus p of x equals 0, which is a 1 minus f of 1, f of 0. Okay, so now, yeah, we're back to textbook, and then so we're going to learn the mean and variance. So I'm not going to prove this, okay? So the expected value of hypergeometric distribution is n times p. Okay, this is exactly the same as the expected value of binomial distribution, right? And the variance is going to be n times p times 1 minus p times this fraction. So without this fraction, by the way, we see that without this fraction, that variance is going to be exactly the same as the variance of binomial distribution. So what is this then? Well, we have to multiply this. I think, yeah, so you may feel that, I mean, everybody's, you and I just feel that we have to, invariance of the hypergeometric distribution must be different from the binomial distribution, right? So not just n times p times 1 minus p must be multiplied by something. So this one, right? So that fraction is called the, you can say, the finite population correction factor. Okay, so because in a binomial distribution, replacement is allowed. Okay, so that's the this one fraction correct the variance of the binomial distribution to fit the variance of the hypergeometric distributions. Okay, so I'm not going to explain in detail. That's beyond of this subject. So we just offset this formula and then apply. You can you just apply this formula. So the exam 3.25 is just question is to find out the expected value and variance of the example 3.24 using those formulas. Okay, so this is algebra. So now then the so that's the all of the 3.7. So next time I'm going to cover 3.8 Poisson distributions. Let me stop here.